Today I'm going to talk about medical imaging. So let's get my screen up for you. Okay, so we're going to look at X-ray imaging, we're going to look at ultrasound imaging and magnetic resonance imaging. So there's quite a lot to do, and I'll try and get through all of those three things. That's not all of medical physics. I'll do the rest of medical physics in a part 2 that will follow. Okay, so X-rays. X-rays are very, very short arrays, and the wavelength ranges from 10 to the minus 13 to 10 to the minus 18 meters. We use the equation E equals HF, and we substitute F for C over lambda to get an equation that relates the energy to the wavelength of the wave, so HC over lambda. H and C being constants and lambda being inversely proportional to the energy. So if I show you an example here, if we have the energy in joules, then we just substitute Planck's constant 6.63 times 10 to the minus 34 times by the speed of a wave, an X-ray, which is the same as the speed of light, 3 times 10 to the 8. And then divide it, say, by 10 picometers. So I'll do it for a wavelength of 10 picometers. So that's times 10 to the minus 12 meters. So divide that by 10 times 10 to the minus 12, and we get the energy in joules of 1.99 times 10 to the minus 14 joules. But that's not actually very helpful for us. So what we tend to do is we convert that into electron volts by turning the joules into electron volts by dividing by the charge of an electron. So I'll do that, and then it perhaps will make a little bit more sense, and we don't have all of these very small numbers. So divide that, 1.6 times 10 to the minus 19, and that's equal to 1.24 roughly times 10 to the 5 electron volts. So roughly speaking, that is 100 kilo electron volts. Okay, so this will become important when we look at how to produce the X-rays, which is the second point. Okay, so we use the X-ray tube to produce, we heat up a cathode with a low current, and we get the electrons, we heat up the cathode such that the electrons are ready to leave the cathode. They've got enough energy, and then they are accelerated across a very high voltage onto an anode, and as they collide with the material in the anode, they produce these X-rays. So we have to apply a large voltage to accelerate those electrons to get them up to a high speed in order to produce these X-rays on impact. So those electrons collide with a rotating anode, and that causes the heat that is generated to kind of be dispersed, and it causes those X-rays to be emitted. So from the equation from energy in electron volts is equal to Hc over lambda, we can see that if we relate that to accelerating the electrons across a voltage, okay, then what we have is, and if I just get the electronic charge underneath, we've got V for voltage equals Hc over E lambda. So if you increase the voltage that you apply across the cathode and the anode, the wavelength is reduced. So the greater the voltage, the smaller the wavelength. You'll notice that Hc and E are constant. So the voltage applied is inversely proportional to the wavelength. So for, as we saw, 10 picometers, we need around about 100 kilovolts in order to accelerate the electrons to produce that sort of X-ray. To increase the beam intensity, the temperature of this cathode here has to be increased. It needs to be higher so that we have more electrons that are available to be released per second. So we increase this cathode current here to increase the beam intensity. So there's two things that we can do here to control the wavelength of the wave and the intensity of the beam produced. The use of X-rays, we use high energy and low energy X-rays, and that will kind of hark back to your voltage and the wavelength that you can produce. And one of them is to produce high, low energy X-rays are used in the diagnosis of imaging. Whereas high energy, and you can see there that bone is very good at absorbing those X-rays, and you've got this contrast between the bone and the soft tissue, so that you can see quite clearly if there's anything wrong with the bone structure. So we can, without cutting open the body and in risk of infection, we can use X-ray imaging to look inside the body without a risk of that infection. The high energy X-rays, so that means using smaller wavelengths, and we're looking at 200 kiloelectron volts instead, is used for killing cancerous cells, for treating cancerous cells in a course of several months of treatment, so that you can kill the cancer cells, but also it will kill living cells, but it gives them a chance to recover before the next dosage of high energy X-rays on that target area. In imaging, so that's for killing cancer cells, as radiotherapy, and internal imaging is using around about 330 kiloelectron volts, so low energy X-rays. Okay, and okay, moving on. So that's for radiotherapy there, and imaging here for lower energy. Okay, now you can see that bone has, it absorbs 8 times more than soft tissue. And now we're going to look at that attenuation, that absorption property of the X-rays as it passes through the medium. So basically, X-rays are incident onto some tissue, and how far it can get through that tissue depends on this quantity called absorption coefficient. So how much, so the intensity of the incident ray is how much is going in, and then the intensity at that particular depth of X, all right, depends on that absorption coefficient. And that's dependent on the energy of radiation and the material itself, the atomic number. So for example, I'll give you an example, 1 mega electron volts of radiation, okay, on tissue with an absorption coefficient of 7 per meter, all right, and we have to calculate what X is for a thickness of I to reduce to by half, so that it goes from I0 to I divided by 2. So we don't actually have to know what the original intensity is, because that is, so we can express one in terms of the other. So I naught over 2 equals I naught, and substitute it into that logarithmic equation, minus mu x, okay, and then this bit will cancel. And if we bring that top level down by logging that equation, we get log of a half is equal to minus mu x. But because we've got that negative sign there, we can bring it over onto the other side, and we can have log 2. I'm being very simplistic. I'm going through it, otherwise it's going to take, I think, too long to get through everything else. But basically, if you have a minus there, you can just swap those two numbers over. So mu x, so log 2 divided by mu will give me x, the thickness. We know mu is 7, so log 2 over 7, 0.693 over 7 equals 0.1 roughly meters. I should have more significant figures, but roughly that is around about 10 centimeter depth of tissue for the intensity to reduce by 0. So we can use the X-rays to look at soft tissue. So if we consider that bone, where are we? Yeah, okay. So I'll address the first part of this, the next part, the use of X-rays in imaging soft tissue. Bone has an atomic number of around about 14, because you're looking at calcium, you're looking at phosphorus, whereas soft tissue has an atomic number of around about 7 atomic number of around about 7, so kind of like half. So you're looking at carbon, hydrogen, and oxygen. So X-rays can travel much further before they are absorbed, because you can see with this equation here, X is inversely proportional to the absorption coefficient, and the absorption coefficient is dependent on the atomic number. So we can use, X-rays travel further in X-rays in soft tissue, soft tissue, before it's absorbed. So we can use these for looking at mammograms, looking at breast tissue. We can look at it for chest X-rays. But very often we need a kind of contrast media to distinguish between different soft tissue. So we use fluoroscopy, where we have what we call a contrast media. And in this case here, we are using a barium meal. So barium has a very high atomic number. We can also use iodine, but for digestive systems, we use barium. It's got a high atomic number. That is going to be absorbing the X-rays, allowing us to distinguish between different soft tissues within the body. It allows for, so we call that a contrast media. It allows for real-time imaging. So if we give somebody a meal, a barium meal, and allow it to kind of like go into the digestive tract, we can track it through the system. So we can see, we can video, save that as a video to look at later, but we can actually see what's happening as the process of digestion is happening and see where there are any blockages. And you can see kind of like in this area here where it's much darker that there's some sort of blockages going on, and you can see that there's a constriction on the right hand side, so that there's some sort of difficulty with the barium meal getting through. Okay, so you can have a before and an after image, you know, as well, with and without the barium, to enable you to look for the blockages. So barium sulfate is the meal that is consumed, and the other contrast media that is used in other imaging is iodine, and that is used to look for blood flow in image angiograms around the heart. So it's looking at iodine being injected into the blood and looking at heart images. It's not really through the heart, but it can do through the heart, but it's around the heart, the images there. Okay, so in order to look at these kind of like in more detail, and we use what we call a digital image receptor, and the X-rays are received. So the X-rays come in on this input phosphor. All right, and you do need to know the construction of an image receptor. And those X-rays will kind of like go through this photocathode, and it turns the X-rays into scintillations of light photons, and those light photons then produce electrons that are accelerated then by the electric field. These electrodes, they're called electrostatic lenses here, but basically they're just accelerated and focused onto an output phosphor. So it reduces the image, which is then connected to a computer for you to analyze it. This technology originated from the detection of particles in the Large Hadron Collider in CERN, but it's basically the X-rays collide with a scintillator producing light rays. It's just basically light pulses, and those light pulses then will create electrons, and in the photocathode that then are accelerated onto an output phosphor at an anode. So you need that potential difference to be able to accelerate them, and then you need focusing lenses to focus them to a point. So we have then the CT scanner. The CT scanner then, the advantage of using something like this with a digital image is the fact that we can get the images very rapidly. So you can get rapid image acquisition, and you can then transmit that information and store that information for future use or for other consultants to have a look at. And you can enhance the image. You can play around with the image so that you can kind of like color code the different areas and the different signals that you're receiving. So we get images, we can then kind of like from that connected to a computer, we can then layer the image and create these 2D images around the body. So you can see the shape of a CT scanner here. We can image in this direction, we can image in this direction, we can image in this direction. And by creating these images at slightly different layers, by moving the table through the donut structure, we can create these a much more 3D image. So the advantage of using computer tomography is to be able to put all of those images together digitally and create a 3D image. Okay, they're produced quickly. The images are produced quick acquisition, and it allows you to identify the location of, anything internally quickly. So these CT scanners are good use for accident and emergency to identify images quickly in order to know where to put the patient and what to do next with that patient. So your standard x-rays, so with the standard x-rays, you have high definition of the bony structure, all right, a moderate definition of the soft tissue, because of course x-ray passes quite far through that soft tissue. But if we use a barium type meal and use we use something that has got a different atomic number, then we can distinguish between areas of soft tissue. CT scanning, though, instead of producing 2D scans, we can now put them together to produce 3D scans. It's good for locating. It's got a moderate definition on the soft tissue. We've got better systems now that look at soft tissue, but it does allow you that contrast. But for both, it's not suitable for pregnant people, because the x-rays are ionizing radiation and it could disturb the development of the new cells growing. So and also with CT scanning, you need the patient to be able to be still, so it's not suitable for somebody suffering from dementia or very young children. Okay, so now let's move on to ultrasound. Ultrasound is not ionizing radiation, so that's one advantage straight away. It's very safe, and it is used for looking at fetuses inside the body. Now, before we do look at that, we'll look at the generation and detection of ultrasound using piezoelectric crystals. So basically what we have is an alternating PD, and that alternating PD matches the resonant frequency of this piezoelectric crystal. It makes the crystal vibrate, and in making the crystal vibrate, you are transmitting an ultrasound going out. But at some point, that then has to stop, because if you interact this electrode with a medium that the ultrasound can pass through, at any boundary, that ultrasound then will come back. So we have to stop the electrical supply, we have to stop the AC current vibrating the piezoelectric element, and get it to be very still very quickly. And this is what the damping medium does. The damping gets it to stop very quickly so that it can receive the returning ultrasound after being reflected at a boundary between one tissue and another in the body. And as it does this, the beauty of the piezoelectric crystal is that when it is pushed or deformed by the ultrasound coming onto it, it generates an AC. So not only is it acting as a transmitter of ultrasound, but it's also acting as a receiver of ultrasound. And it's all to do with this piezoelectric crystal here that can generate a current when it's squeezed, and alternatively, when you apply a current to it, it can change shape. So that's why, and you can use piezo crystal in your ignition of a gas lighter. If you I really have gone over very, very briefly of that. basically PD applied to it makes it expand in one direction. A PD in the opposite direction makes it expand in the other direction. So that's how you get the ultrasound out of it. And this creates the ideal crystal here is quartz, is what is used. The ideal is a wavelength over 2, is the thickness of that, of the ultrasound that you want going into the body. And there is an acoustic window that will allow the sound through this layer so that it can go into the body. And we can produce different scans. So you can produce a scan where there is just literally one dimension, and we can determine the difference in density between the different boundaries of tissue. Or it can produce a B scan where you've got a series of A scans and you put them together so that you can have an X direction image as well as a Y direction image, so that you've got your X and Y image, whereas the A scan will just give you one direction, let's say the Y direction. So that the B scan can allow you to kind of like look at what's happening across as well as what's happening at depth. And this plays on acoustic impedance, i.e. the absorption or reflection of the acoustic, the ultrasound wave. So if we have an incident wave onto a boundary of 2 different mediums where the speed of the ultrasound is different, then some of it will get reflected and some of it will get refracted into the body. And that's dependent on, acoustic impedance is dependent on the speed of the sound and the density of the material. So the denser the material, the higher the impedance, the absorption of the ultrasound, and the higher the speed of sound, the higher the acoustic impedance. So we are interested in, so the amount of reflection, it depends on the amount of acoustic impedance. So we have this, so the greater the difference in acoustic impedance between the 2 different mediums, the greater between the 2 materials, the greater the reflected portion that you will get. So for example, let's just show you a few examples and hopefully this will become clearer. For an air to fat boundary, so that's from outside the body and going into the fat of the body, the IR ratio to I naught, the reflected incident ray, how much is reflected to how much goes in, is equal to 0.99. So we say that 99% of the incident energy is reflected and little, therefore, will enter the body. So this is why we need to have a couple. So the transducer must be coupled. And it's coupled using a gel between the ultrasonic probe transducer and the skin. So you'll see that the practitioner will put gel at the end and push down hard onto the skin so that there is none of this reflection and the majority of the signal goes in and is refracted into the body. So for the IR for the bone tissue boundary, it's 0.41, okay, for the amount reflected to the amount that's incident, which means that 41% is reflected. That means the rest of it is refracted into the body to enable a scan to be produced. For fat muscle, it's 0.01, which means that 1% is reflected, and the majority of it will go and be refracted into the body. Even better, because what we want is we want it to get in there and to get into the body. But beyond bone, nothing can be seen. So for that fat muscle, for any to be reflected back, what we need is a full bladder, so that there's a greater contrast, a greater difference in the density but at the boundary, so that you get some sort of reflection at the boundary to show a contrast. So the full bladder is needed to show some sort of contrast. So on the one hand, you want it to go in by refraction and you want little reflection, but at the boundary of the different tissues internally, you want it to be reflected so that you can receive a scan back out. So hence a full bladder is needed. We can also use a Doppler effect. Now, you've used the Doppler effect for space and looking at rotation of bodies orbiting, and looking at them going away and coming towards, and a detection of other things around distant stars. And that would have been in Unit 4, so earlier this year, hopefully. Now, this is used to looking at blood flow using ultrasound. It's used to study the speed of the flow of red blood cells, and there are two Doppler effects taking place. One where the red blood cells receive the signal, because don't forget, the red blood cells are moving in one direction and you're sending a signal out, but it's also moving. So that's one Doppler shift. And then as it reflects back, it's also moving in the same direction, but it's being reflected. So on that reflection, the wave received would have been shifted somewhat. So this is why the 2 is in the equation. So we can use change in frequency over the incident frequency is equal to 2 times, because you've got 2 lots of Doppler effects, V over C, and we can approximate for small angles. We can use that approximation that cos theta is roughly equal to 1, and we don't need to include it. That's for if you manage to get the transducer in the right place and that the angle between that ray and the direction of the blood flow is very small, and as you can see here, it's considerably larger. But you are looking at it radially. You're trying to get it as close in line to the blood flow as possible. Now, the advantages of using this is that, and C is the speed of the ultrasound, and V is the speed of the red blood cells. And the change in frequency is the change in frequency received back of the incident frequency going outwards. So this is like your incident, and this is the change in frequency because you've had that Doppler effect twice over because of the reflection. Speed of ultrasound. Okay, I'm very aware. I know I need to move. Right, real advantages. Now, you can get real-time images here of looking at the blood flow. You can get 1D and you can get 2D scans. That's scan A and scan B. There's no ionizing. That's got to be the most important one. No ionizing radiation here. So it's safe in terms of it's not going to ionize any cells. And it's relatively low cost. And this applies to everything to do with ultrasound. The problem is that so those are the advantages. The disadvantages are that it's not a very high definition of image compared to other techniques that we have got. And as soon as it hits the bone, you don't get any imaging further on. So you have to kind of like, if you're going to do any blood flow around the heart or near the heart, you're going to have to really put that probe in between the rib cage, the ribs. Okay, moving on to the last one, magnetic resonance imaging. This one is giving us much higher definition, but the images need a long time to be acquired, and there are restrictions on using this magnetic resonance imaging because we don't want anybody to have any metal inserts with that. Okay, now this is complicated and there are 3 or 4 things to consider. Okay, so I'm going to go through the principles. Neutrons and protons basically have a spin, okay? And if there are equal numbers of neutrons and protons, then they'll all cancel out. There's no net spin overall. Now, those elements that have odd numbers, for example, hydrogen, that just has 1 proton, or phosphorus, carbon-13, they have odd numbers of protons and neutrons in their nuclei, so they will have a net spin, and I'm just going to focus on hydrogen. All right, so if they have a net spin, that means that they have a north-south axis. Now, normally the magnetic properties of hydrogen are all randomly aligned all over the body, so again the net effect is 0 in all directions. But if we place it in a strong magnetic field, these nuclei then will all align themselves. And now these nuclei are called precessing nuclei. And the magnetic axes of the nuclei rotate in the direction of the external magnetic field. So this is an atom, hydrogen. This is the proton of the hydrogen in the nucleus, and you can see that this will be north, this will be south, this will be the north end, this will be the south end. And the nuclei has 2 states. There is a lower state in which it can spin, or there is a higher state. And what we can do is we can put a radio frequency pulse into that nuclei, and we can flip the energy state from the lower energy state into a higher energy state. And they're all aligned then at this higher precessing, all aligned at the higher state. And the frequency that happens is a special frequency called the Lamois frequency. And the frequency is dependent on the magnetic field. And frequency is given by 42.6 mega times 10 to the 6 B. Now, that is dependent on the magnetic field. So the frequency, I'll put the units there, And I'll put that in brackets because I want you to be aware that the frequency is proportional to the magnetic field strength. And that is the key, because the Lamois frequency across the body and down the body will be ever so slightly different because we change the B field across the body and down the length of the body. Okay. When the radio frequency pulse stops from, kind of flipping and getting it to align in a higher energy spin, then it will relax down. The spin state will relax down into the lower energy state. And in doing so, it releases a radio frequency pulse that now, what was once the transmitter, now acts as a receiver in the MRI imaging equipment. So it can receive it, and it tells the time, or it calculates the time when it receives that signal back, when it stops sending it off in the first place. Complicated. Basically, you just have to remember that all of these nuclei, single protons, they have a spin. When they're placed in a magnetic field, they all line up. That's the precessing bit. Then when you apply a radio frequency pulse, you flip them into a higher energy state. They're all now precessing in that higher energy state, and then it relaxes back down. But the times of relaxation back down are different for hydrogen bound in different mediums. So, for example, and this is called the characteristic time, and this is what the machine is doing. It's picking up that radio frequency when it relaxes back down, but it's measuring the time it takes to come back. And that is a characteristic relaxation time dependent on how the hydrogen is bound. Okay, and we call that T relaxation time. And it's different for different things. So for hydrogen bound in cerebrospinal fluid in the brain, i.e. water in the brain, it's 3 seconds. T equals 3 seconds. But for cerebrospinal fluid, it's 3 seconds. But for brain matter, or brain tissue itself, not the water, but the tissue itself, then the time is 100 milliseconds. So by finding the times differences between the radio frequency pulses that come back as a result of relaxing back down to a lower state, we can match where those different materials are. Okay, so we can now use the MRI in terms of obtaining diagnostic information about the internal structures. So we can, again, use the idea that you are taking information, because we change the B field across as well as down the body, then the Lamois frequency is ever so slightly different. And that frequency is detected by the same coil that produced the radio frequency pulse. So you'll basically flood the body with slightly different frequencies, and you'll get the image back, you'll get the information back of those frequencies, but at different times depending on the tissue that it's coming from. So that's the secret to have a non-uniform magnetic field along the body's axes and radially, because we know that the frequency is Lamois frequency, okay, sometimes with a little l, is proportional to the magnetic field. So the different tissues can be located along the length and the width. So we can get whole body scans, or we can get functional magnetic resonance imaging scans where the person has got, say, headphones on, and they're asked to think of different things, or they're asked to do different things. They have to keep the head very, very still, but you can look at brain imaging and the difference in areas that is affected by the different thought processes going on or the different actions going on. If people do suffer from claustrophobia, we can use an open MRI now, but this does affect, people suffering from claustrophobia or dementia. But it does give you very good spatial advantage. It does give you very good spatial definitions. It's good for soft tissue, but the disadvantage is that the image acquisition takes time. So disadvantage, it's very expensive. It's much, much, much more expensive than CT scans. It's longer to get an image. The longer you're on that bed, the better the image. We can't use any metal inserts because you have got this very strong magnetic field. And once again, the magnetic field, the magnets used, the technology for that came originally from the CERN technology in accelerating electrons. It's not for young who can't keep still. So not for young children, not for dementia, people who suffer from dementia or claustrophobia. But there's no ionizing radiation once again. So the effect on the body with radiation damage is non-existent. Okay, all right. I think I've managed to do it. I don't know how, but the advantage and disadvantages, I've tried to do it as I've been going along for ultrasound, for X-ray imaging, and for MRI. So we've done a very brief synopsis of MRI and the uses of MRI. We've looked at ultrasound, looking at fluoroscopy, i.e. studying blood flow, looking at A scans, B scans. For example, there you can see into the eye, coupling agents, and looking at this equation for reflection to the incident ray. We've looked at ultrasonic transducers, we've looked at CT scanners, image receptors, fluoroscopy to intensify the image, and standard X-rays, production of X-rays, and characteristics of X-rays. So I think I'm going to stop sharing this window and stop. And next session, I'll go on to medical part 2 and looking at the effects of radiation on the body and looking at PET scanning and radiotherapy.